For this photogrammetric point cloud processing training, we will use data from Video Drone Finland. The data set was collected with UAV GeoDrone, and the point cloud was generated with Pix4D software. So it is an example of photogrammetric point cloud. If you're interested in project location, it is Finland, Jyväskylä city. Shortly about photogrammetric point cloud. So photogrammetric point cloud basic requirements are texture, suitable brightness, and overlap. It has to be some textures on the surface to create photogrammetric point cloud. Then image brightness should be suitable. It means that too dark or too bright images impact point cloud quality and make it worse. It must be also some overlap, at least two images see the same spot, and by increasing the overlap using more images, result becomes more reliable. As an example output, reliable measure the points come from well-textured surfaces, those locations covered by good image overlap, and it was suitable brightness of used image. Less reliable, worse results comes from places where you're lacking information. It is reflection or not enough light, brightness differences exist. And as a result, points were calculated mostly by interpolating from surroundings. Also, each software uses its own algorithm, so different softwares produce quite different looking photogrammetric point clouds. As I mentioned, the sample data that I shared with you is generated with Pix4D software. And the demonstrated workflow doesn't fit, like you can test, it could fit to your own photogrammetric point cloud, but maybe you need to change some settings to adapt to your data. Now about the challenges in this Pix4D generated point cloud. In comparison with LiDAR data, in LiDAR data usually exists constant noise level. If there is plus minus 3 centimeter noise, it is same everywhere in all point cloud. But photogrammetric point cloud noise level changes a lot, and different locations could have different noise levels. To solve it, we will run one macro which contains classification of surface points and then smoothing points. First one classifies surface points, removes noise, and keeps just the local surface points. Second step, the smoothing would smoothen XYZ, and this smoothens surfaces by changing XYZ coordinates of points. So that surface becomes sharper. Another challenge in this data is high density, and as high density not always the bad thing, like you have good visibility of everything, but this gives a speed issue. everything runs slower if you are using all points as in for the active classification. The suggestion would be to move some points to unnecessary density class. It can be done in thinning step, for example. Then do all classification on the active use points, and after the classification is done on those actively used points, then there is a possibility to copy classification and group assignment to that unnecessary density class. So all points that you have would be classified. So that was short introduction about the data, about what challenges you can have with photogrammetric data. And now we can move to the sample data to open the DGN and load the point cloud to observe what is inside. I hope now everybody has this photogrammetric folder that I sent a link to you. And I created DGN file for Bentley platform. So if you're using that, just open this file. In case you decided to use SpaceX, then what you need to do to create a new design file. As Bentley platform suggests which seed file you want to use for the design file, SpaceX asking you to specify the template. And basically you need to choose something similar as seed file. They are stored in Data60 installation folder and then seed folder, and it's named seed 3D centimeter or seed 3D millimeter. Choose, I think, centimeter. The centimeter and millimeter talking about the resolution, so it depends what kind of resolution for the coordinates you have. For mobile projects, probably millimeter level can be used. In airborne data, centimeter. The same thing is for microstation. If you pay attention while creating a new DGN file, then you see that the last row in that new creation is to specify which seed file to use. So again, you need to go to that Data64 installation folder and in seed folder to search for required seed file, either centimeter or millimeter. So while in SpaceX you're creating a new design file, choose the seed, and the file will be created according to that template. And now just name your new design file. If you don't have data applications loaded into SpaceX, then you need to go to iXapps and execute. From here, you need to go to Data64 apps and load DataScan and other applications into SpaceX. So it's similar as in Bentley platform in case you open that DGN file and you are not able to see any data scan tools. Then in MicroStation ribbon, there is utilities and MDL applications where you can load the needed application. Reading points in MicroStation is just you search for the floating main dialog of data scan, go to file and read points. And then search for raw point cloud folder in which it's stored that LAZ file. In case you are not able to see anything, then maybe you need to choose all files to be visible. And then pick that raw point.laz file. If you're using this platform, all you need just press OK. In case you're doing this with SpaceX, then there is additional step, so you can do also that read points, but don't load it, because what you need to do in the beginning, you need to define the range of the coordinates, so the software would know the limits. And this read points dialog gives you the preview of the coordinates. So I see for the north thing is something around 7 million, and for easting is around 400,000. If you had this read point preview, just cancel, and before reading points, search data scan step scan define coordinate setup. It is in the toolbox of data scan, the first icon, and if you keep it, press it and keep it longer so it extends, and choose the second one. You need also to change the resolution, because here was, as I remember, I chose centimeter seed file, so resolution should be according to that. Then for the easting, it was something around 400,000. Northing, it was 7 million, if I remember well. So type those values in. It was under the first icon. And then define coordinate setup, 100, 400,000, and 7 million. So now the range is defined, and we can repeat the step for reading points, and that raw point cloud. Originally, this data was processed in LAS format, I think. Just I saved in compressed LAZ format. This compression saves a bit space. But basically, in both formats, the softwares like these formats, they have the mandatory fields. And for example, for each point, it records echo, line, mirror angle, values, but actually photogrammetric points, they don't have those values, and just because of the format requirements, it was recorded. You can also unselect those not existing values to so it can be a bit faster, and probably it would save a bit space not reading the values that doesn't exist the color and XYZ and class. So basically from those two just leave the color on. It says for me that actual resolution was 1000. I was choosing 100, so my coordinates will be rounded to 100 resolution. But in case you wanna have the full quality, then actually in this case, millimeter seed could be selected. And MicroStation, as I mentioned, is more simple, so you just read the points and that's it. This coordinate range definition can be valuable in case you try to read points and somehow they are outside the range. Then you need to define according to your point cloud coordinates. So now you can see some points. Read it in. Buildings, trees. We can investigate a bit the noise level. Also for the preparation, we can load the class file to have the same classes, and then for sure everything will go smooth in the macro steps. To load the class file, you need to go to Scan toolbox and search for Define Classes option. And open the file from the folder which you downloaded. Search for hippos.ptc file. It is at the same Photogrammetric folder. Now we can see which classes are predefined. Also, according to the class, each class will be colored by particular color. I will close this. We can also investigate if there is any classification done. So in Tools and Show Statistic, software would generate a report. I see that at the moment all points in class 0. Now we can also look into data visually, so we can change a display mode to display data by color. In the main data scan dialog and view, you can search for display mode, and then in view 1, so I have my top view in view 1. I want to color points by color. If I click apply, I have a better understanding of this data set. So we can check, for example, what kind of surfaces gives the noise, more noisy. This dark roof looks quite splashed. If I do this vertical section, I can also define I want to see immediately in view 4. The asphalt looks quite okay. We can check also our white buildings, how it was processed, surfaces in that location. So this gives understanding for this that actual dark surfaces are more noisy. And then if I check here the section near the water body, I see that some world under the ground surface exists that it shouldn't exist. So we looked a bit on the different situations, how it appears in the point cloud. As I mentioned in the presentation, it also matters how well the point cloud, the image sees the locations. So for example, here was something like a shadow that was not captured from all sides. There's a gap in the data, and also because of the interpolation, it is more noisy. If we have dense vegetation, also I'm not sure if this can be called as a ground surface. And after this short investigation, we can start with classification. First, we can do classification everything to the default class, which will be used as a main source for the next steps. To do that, we can do just as a simple routine by class from the data scan dialog. So search classified, then routine, and by class. This is quite simple step, and you just say from which class to which one to classify the points. So if you find this one, click. It opens the dialog for classify by class, and then we can choose that from any class. Software would drop everything to default class. Click it OK. And I got the indication that 56 million points were classified into that default class. If I go now to show statistic, I see that everything now is in the default class. Another thing what we can fix is water body. Usually water surface is generated quite bad in the photogrammetric point cloud, and what can be done, just simple classification inside the polygon and then manual improvement of the classification. If you are using MicroStation platform, just select the shape from second level, which you already have in the design file. In case you are using SpaceX, then you need to draw that shape by yourself. And it can be done with this place polygon, I think, tool. Yes, it's called place polygon. And you need to go around this water body. Place polygon and then go around. After this, choose element tool and select this drawn element. Now, if everybody already selected, click it, select the shape, and then search for another tool, classify inside fence. In this case, let's classify from default class, the main source class in this point cloud, and then to 15 water class. Click OK. And by this step, if I do a section now, I see that the water points got a blue color, and it is classified into the water surface. Now, after this classification inside the polygon, we could also improve the classification by adding more points to the water surface by just doing the sections and seeing if it's something really under the surface. So for example, here I have some artifacts. Those I would like to classify as well to the water surface. And for this, I will use manual tool. It's could found in under the fourth icon. So if you press and keep it longer, search for classify below line. And then I would choose from default to water surface. So just draw the line, and like this, points can be classified below the line. There is something more here. Can be done the same for this. Yeah, so if I would say I'm already happy with this classification, so it's enough for me, the editing. If you done some points, then you tested the tool. And now we can save this edited point cloud as another file. Go to File and Save Point As. I want to save everything, and in this case, I'm choosing fast binary format. This doesn't save the 0 values that last file, for example, saves. And click it OK. Now that we've done some investigation in the point cloud, as well manual editing where the big errors occur as near the water surfaces, we can move to ground classification of this point cloud. For this, go to Tools and Macro. And go to File Open to pick the macro from Macros folder, and then the first one, Ground. This one, either you can just run on loaded points, so the software would run everything on loaded points, each line. Either you can step together with me and we can go through the steps with a bit of explanation of each. First step is sort the points, and if I edit, I see they will be sorted by XY location. If I check the neighboring points, I see that they are not next to each other. The sorting step would sort a bit, and then the consecutive points from the same place after this step would be in order. And by having the coordinates sorted, it would speed up a bit the later steps. So press it step. And now if I would identify points, they would be closer to each other in the list. Now after this step, let's see if I is isolated points classification. So if there is some single point in the ear that it is not anyhow helpful in further classification, this can be removed with with the isolated points classification. Cannot find any. I will make points thicker in the section view, so it will be maybe better visibility of this classification. So isolated points, if you step, it should remove some points without neighbors, and then that isolated points also can be deleted because they are not useful. So I'm going to process the third step. I see those disappeared from my display. Now this classify surface routine would pick surface without so much noise. It keeps the local points which matches to the local surface. And routine also searches for horizontal, vertical, and sloped surfaces. So points kept in the default class represents more noisy data. It's still running this step. And these first steps in the macro, they are more for removing noise as much as possible, and keeping more points that belongs to the surface, to the clear surface. Now I see the blue points got inside that surface, and I see that the white points around the noise left out of this classification. And this was the aim of this step. Now the next is smoothing. So it takes some neighboring points and then modifies this blue surface points by X, Y, Z. I step also that smoothing. Smoothing is local, so it doesn't make the surface total planar and still keeps the features. Now I can see it's thinner, this surface, it's not so fat line. So from what was before, I have clearer surface of the ground. It's also for, as I mentioned, for the vertical surfaces the same. So it smooth a bit the walls, the roof as well. Now step also the endpoints. This step will put some unnecessary density to the separate class. And now if I in the view for turn off the unnecessary density class, I see much less points. Also, this step with the unnecessary density class exclusion will speed up a bit the process. Then click on the hard surface classification. And it would give the surface and the final surface which would be used for the ground classification. So if in LiDAR data ground classification is quite straight, in photogrammetric point cloud, as you can see, you need to make quite many preparation steps to remove the noise. And now those red points, they are potential ground. As you can see, most like it got also on the roof, but basically it follows the ground surface. And from everything what was as a ground, this fat layer of points. Now if I change and just keep those potential points, I can see quite cleaned point cloud. Now it's either straight to ground classification step, or you can add a couple additional steps to use also vegetation index to classify the ground. Because the point cloud has a color information, you can use the tool compute distance and then compute visible band difference. This has built-in vegetation indexes, normalized and visual band differences, and as it requires true color, photogrammetric point cloud has it. It can be used. The distance value is expressed how likely a point belongs to vegetation. So larger positive value or larger negative value, and distance values range between -1 to +1. After all these vegetation index distances values may support the vegetation classification of photogrammetric point cloud. So now I step to compute this distance, and if on the top view I used to display by visual band differences, I see what the software understands as a most likely vegetation and what is not. This information later can be used for ground classification, as I mentioned, because especially in the photogrammetric point cloud, sometimes it is hard to understand where is the, for example, here I did the section and actually my ground is here. Here is more like low vegetation, so not so much change in the surface. But this vegetation index can be used in ground classification step to guess that. Then there is a smooth endpoints action. The smoothing will be done for the distance values, and the reason for this, the color is noisy and vegetation index becomes also noisy calculated from that color information. So this could smooth a bit, and now then the vegetation index is classified. We can move to the ground classification. In this step, like we will use that 6 class. I just used the building class for that. It is more, in this case, it doesn't mean that it's buildings. It's more as a helping class. So I reserved that class for those potential ground points. Later, I will clean up that 6 class. And what is important in this classify ground is use distance as a rating. And if you choose that option, calculated vegetation index will be used for the classification. And the logic under this is that green point is less likely to be accepted as a ground, less possibility the ground classification would climb up on the vegetation. And this weight setting, it acts as a probability factor. So 1% is the small use of vegetation index value, 100% is like use as much as you can, something like this. The default is 50, I will keep it, and I will run ground classification. Now I see the ground classification was done for me. I will do by class and just display the ground points. So this is the final result, what I got as a ground classification. In case you need to reach quite good accuracy of the ground classification, it is possible also to edit classification manually. So the same, you can do the sections to see if some low points were classified or something. Also, either you can display it as a shaded from the display mode, and this surface would give you a understanding if you have some completely low point that you need to fix or some holes in the surface. But for this data set, I would say it is reached quite good result of this ground classification. And for the next, we can move to above ground features classification. After actually step by step I ran all macro, I will save points to have these changes saved to the point cloud. And search for macro in the same macros folder, this called second features. Open it. So in the view, I will do by class, except unnecessary density. Now it's quite messy. Maybe by color. And now you can press run on loaded points. So the macro step would run each step on this loaded points and to classify everything. The first steps in this macro classifies those helping class, the potential points for ground back to low vegetation. Then the best approach for above feature classification is the use of grouping and best match. For grouping step, the software requires you to have distance calculated. For me, it's done. So I will open some steps to explain. As I mentioned, this compute distance should be done in order to be able run assign groups step. Also, computed distance for each point from the ground. It can be used for data classification into the layers according to the high from ground. For example, low and medium and high vegetation can be sorted by this until 2 meters. Medium was done, and more than 2 meters high vegetation. About step to assign the groups. So this command assigning groups to the points. The grouping is then based on different methods. Depends what do you want to group. It can be done by plane fitting, watershed algorithm, or 3D spacing between points. In this case, we want to classify quite many classes according to the grouping. So for example, buildings, they are done with plane fitting method. Watershed algorithm is helpful for trees. detection, and then by density can be seen other objects as cars, for example. A method for grouping trees, there's two also by highest point. So this method is based on watershed algorithm that starts with highest point and then searches where that tree is ending and starting another one ways, again rising to the highest point. Another option is trunk. This is based on approximately circular tree trunks visible in the point cloud. So this requires a high amount of points from trunks and suitable for very high density airborne point clouds or mobile data. So this was about the methods for assigning the groups, and this classification by best match is simply you just choosing which features you want to classify and to which class. This macro already done. So I will go to display mode to check what kind of features I have classified in each class. I have just actively classified points on so that unnecessary density is off. And first I can check what I have in building class. So I got classified those white buildings, some smaller houses, this roof, the darker roof. Also, I don't have those artifacts on the roof, the noise that was visible before. So I see the red point just follows the surface for this one. There is also some mistakes in this classification, as for example, here is the stadium, and those seats were classified as a building, but actually is not. So those kind of things, they can change and be edited by manual steps. Some roof structures were classified, those chimneys and everything what was on the roof to another class. Then there's a wall class. This includes the vertical large enough planar surfaces. It was around each building those walls detected. but there is also some wrongly classified ones. For example, these are just fences that has enough large planar surface. And there is also wall structures, some small details next to the building, and the wall structure, wall and building formulates the full classification of that each separate building. Another class that was classified by this best match is trees. So for trees, it is quite clean classification. Most of the classified points actually belong to the trees. Another thing is car. I don't have any cars, but I remember it was included in the step. Okay, seems I have two classes for cars, so sorry I didn't rename that correctly. So choose the the lower car class. Also, the majority of points in this class, they are cars. Of course, the routine didn't catch some, but the majority was classified. And there is also pose class that tried to search for thin vertical objects. And then there's a vegetation class that tried to classify the vegetation. So this is something that could be taken, like some car should be classified back to the car class. Also some artifacts left in vegetation. So in general, this classification by best match do most of the classification, and then the suggestion is to continue with manual classification steps and editing this classification depending on the classes and project requirements, what level of the accuracy you need to reach of the project. The manual tools would be those classify above, below lines that we already used for water surface classification, like not exactly water surface, more like the noise near the water bodies. And after the classification is done, it's still left that unnecessary density class that actually is not touched by classification. And as I mentioned in the presentation before, that for the density challenge, the strategy is to, in the beginning, to classify out to the separate class, the necessary density, and then in the end to come back to that class and to classify those points by closest classified point. Let's open one more prepared macro that you can find in that macros folder. The third copy class close by. Open that one and run on loaded points. So this macro would copy the classification to not classified points according to the distance. So if there was close point from the car class, it would add more points to that car. And this classification would densify the point cloud, densify the classes, but the only class that is left as it is ground class. We think we are recommending to keep it as it is enough accurate and it's enough density, so it's better not to add more points that can be as a noise. So after using those unclassified points and adding to the classified points, this is the final result of the point cloud that was prepared for today's training. And to sum up, we went through the main steps to clean the point cloud, to classify the surface as potential points for the ground classification, also use the vegetation index to classify the ground. After ground is classified, above ground features can be detected. And as a last step, to classify unnecessary density that didn't participate in the active classification steps. So it speed up the process, but after all, when you copy the classification from close by points, the points still belongs to those classes, so you don't lose the density. So this would be everything what I wanted to say. Thank you for participating.